that are developing capabilities for OpenFlow, SDN, for programmable networking. So that's another reference architecture. And this is some of what we do with this. Each color represents a different science research domain doing different kinds of experiments, successfully all segmented so that the experiments don't interfere. So there's a lot of benefits to SDN. I'm not going to talk about them because by now I think that they're pretty well known. You get granulated views in the network, you get enhanced capabilities for controlling those views, and much more. So SDN is eating the network world. An issue, though, is that it's a single domain oriented architecture and set of protocols. So motivations exist for SDX to, first of all, interconnect SDN islands. You also get better engineering because you get granulated views into all flows through an exchange, and you get control over those. However, having operated in SDX for 2 years, we discovered something else, which is that we can create a high degree of customization for individual science domains within an SDX, which is essentially a large-scale virtual switch. So we've been developing APIs into this capability. We've been developing capabilities for multipath federation, controller signaling, topology exchange services, and much more. An SDX is a large-scale recursive virtual switch within which you can create virtual switches. And that's the big important thing, because each of these switches can be a private exchange for a private community. So one of the communities we've been dealing with to showcase this capability is a joint project with the University of Massachusetts at Amherst. They're developing an application called nowcasting. Nowcasting, unlike current radar, is based on small form factor radar. So they can see over the curvature of the Earth, and they can see the weather in now time versus predictive time. However, they generate so much data, absorb so much data, that you can't compute it locally, analyze it locally, visualize it locally, store it locally. So you have to send that raw data out across the nation at very high speeds. On the left here, you see the granulated views that they get, and it's more of a near-time view. It's more like 6 minutes versus 12 minutes versus the old form factor Doppler radar. It's a very effective technology. What does networking have to do with this? Well, it uses an ongoing, constantly changing topology, and this is a demonstration that we did with a prototype SDX in Georgia for a GEC, a Genie Engineering Conference early last year. This is dynamic provisioning of topologies with the radars on Genie racks simulated over 3 fiber optic networks, ESNet, the I2, AL2S, and the Oak Ridge National Lab fiber network. The constantly changing topologies were successfully signaled using SDN capabilities. So as weather moves, you need to change the topology. So this showed an exchange doing constantly millisecond by millisecond changing topologies. We've also been working with Amsterdam, Netherlight, and Surfnet. They also have a prototype SDX. For last year's Tarina, we did interoperability demonstrations. This year, we also did some demonstrations in advance of this conference to report results back, which we're doing. This time we used the ANA as a data plane, and we used our existing control planes. We're going to continue to develop this. Also internationally, last year we worked with Cybera, and this year we're also working with them, and Martin at the end of this talk will talk about this demonstration. For the Glyph last year, the annual conference in Queenstown, Queenstown, New Zealand, we set up a multi-country data plane to see if we could scale that network prediction application worldwide with sites in a variety of countries, again using simulated radars and Genie racks. And this is the imaging that resulted from that. That was another successful experiment. With the University of Tokyo, we're working on an interesting thing called a slice exchange. So far I've been talking about an SDX as a communication exchange. We're extending that concept to allow for software-defined networking infrastructure to also be included so that you can have other kinds of resources beyond communications extending across these exchanges. This is a block diagram on this project. For supercomputing last year, we had the question, can we also control very large-scale science flows with SDN? We had a showcase at supercomputing to do exactly that. Flows up to 98.4 gigabits per second as individual flows, controlled by SDN. I have to note later speaker Rod here from Siena helping us out with one of the nice test beds. It's a 100 gig test bed. This is some work that we've been doing in this area with the Goddard Space Flight Center. And notice in the lower right and here are servers with 100 gig NICs. So we're doing end-to-end 100 gig flows across the wide area, zero packet loss, long duration, controlled in part by SDN technologies. And this is yet another one of these. This is a 100 gig SDX experiment. We're building an international set of these capabilities. We're working with a number of people in a variety of countries. One of the driver apps that has focused our attention recently is this one. This is the core infrastructure. We have been working on hybrid topology exchange capabilities so that these different SDXs in different countries can both segment the slice exchanges and control them with appropriate policies. To showcase what these can do, again, with science beyond the instrumentation radar demonstration, we put together this. We created a custom SDX within the virtual SDX strictly for bioinformatics to show a use case for personalized medicine. So it's customized medicine enabled by precision customized networking. Imagine this as a large-scale virtual cancer center as opposed to a physical cancer center that can serve patients around the world, including those requiring data flows. So the data that's required to do this application has been stored in repositories around the world, not just in one country, not just at one site, but around the world. And to do customized medicine, you need to find that data, integrate that data, do very complex workflows that normal exchanges simply can't do. They can't support that. What we showed is by using this virtual exchange with sites around the world, including the Genomic Data Commons, the National Institutes of Health, the Ontario Institute for Cancer Research, the European Bioinformatics Institute, you can set up an effective capability for doing unique, customized medicines for unique individuals. This is a very different model than the current medical practice. And these are some of the flows. These are very large-scale file flows. So thousands of small files, hundreds of extremely large files in very complex scenarios. We're also going to integrate this with some cloud test beds. This is one called Chameleon. We're standing up a distributed cloud test bed for computer science research. And this is a bit of a shout out to our friends at ESNet who have an SDN test bed that's in our facility. We're going to work closely with them because they're doing really good work in this area. Also, they've pioneered something called Science DMZ. There's a whole other discussion on what does a Science DMZ have to do with software-defined networking. Unfortunately, today we don't have time for that, but I just thought I would mention it. It's a very cool topic. Another issue is the National Science Foundation has something called the International Research Network Connections Program. We've recently been awarded by the National Science Foundation funding to create an international SDX to work with other SDXs around the world specifically for large-scale data-intensive sciences, and we'll be doing that with many members of the Tarina community. These are some of the participants. And with that, I'll say thank you, and I'll turn it over to Barton to finish up and talk about your, yeah, let's see if we can, well, we can't get it back that way. Yeah.
Closer. Oh, so close.
There we go. Oh, done.
There we go. So, thank you, Joe. Geez, I love that example with the personalized medicine. Just the potential. Okay, how's this?
Perfect.
All right. So I'm from Sibera in Alberta, Canada. And a couple of years ago, we were looking around for some project to do with software-defined networking. We recognized its potential, and our organization, we don't have much interest in inventing new technology, but we really like taking emerging technology and actually working with it and building out pilot projects. So we built this software-defined networking test bed. We wanted it to be multi-vendor, so we can experiment with switches from the different vendors, try out their support for OpenFlow. We work closely with the universities across Canada, and we've had this test bed more or less in place for about a year now, but it's been in a state of constant flux, constant change. The sites, we have a site in Ottawa, two sites in Alberta at University of Alberta and University of Calgary, and another site out in Victoria. And all of the sites are connected through a single Layer 2 network on Canary. The sites are connected. We're using MX80 routers from Juniper and Pika 8 switches. The MX80s are operating in hybrid mode, and that was why we chose the MX80s. And connected to each site, you can see that we have a small OpenStack cloud. It's a very small OpenStack cloud. It's basically just a cloud controller and a single compute node. It's enough for someone to get to that node and create a half dozen virtual machines or whatnot, and try to do something with this, something practical with this software-defined network. What else can I say about it? We have a practical focus for the work with this test bed. We're trying to reach out to network engineers more than network researchers necessarily. The entire network is bookable. We're looking for people who want a software-defined networking test bed. They want to try software-defined networking to see what they can do with it. They can contact us and arrange to have access to some part of the network or all of the network and try to do something with it. As Joe mentioned in a other slide, you can see that we have peering with SurfNet and with iCare. I think that's about it. If you have any questions about this, or you're interested in working with us and doing a project on this test bed, please let me know or contact Joe, and he can get to us. and we can start talking.
Yes, consider this an open invitation to everyone. We want a worldwide SDN fabric, in this case, not production, but rather for testing, because we want to test ideas with all of you worldwide. That's why we're going to have a lot of, well, there's a lot of ideas in this space. Nothing is really solid. It's not quite production yet. It's going to be a while before it's production. So start your test bed, get it interconnected, get some fine folks to try new things, including radical ideas, and let's do cool things. Thank you.
Thank you.
Okay. 10 minutes in advance, and you are two. You will deserve some kind of prize. Don't go that easy. Okay, Joe, wait 1 second. Maybe someone wants to
questions.
Shoot any question to you.
So what do SDNs have to do with software DMZ? Yes.
I have a question about
Kurt, if you mind, just for the people on the streaming.
Yes. I have a question about this SDX. So, is this your interface, for example, to other domains, connecting also further SDN testbed environments, or cloud testbed environments, or is this an interface or a peering point that you will negotiate or exchange or sharing resources from one organization to the other one, or from the private sector to the academic sector, for example?
The answer to all those questions is yes, with the possible exception of the one question about commercial domains. Okay, we're not quite there yet. The closest we got to commercial domains is that joint experiment that you saw in Queenstown. At the time we were doing that experiment, Google had their center of SDX R&D in New Zealand and worked with us on that project. And for them, they said, look, SDN is saving us tens of millions in our data centers, tens of millions in our wide area, but we need to get out of these islands. We need to have an SDX, and that was the center of their development. So we had some discussions about that. But we really haven't dealt with the commercial side. The guys in Georgia, at Georgia Tech, are doing that. They're trying to stand up an SDX that will serve the ISPs, but that's not something we're doing yet. I like your other questions, though, because basically what they highlight is the fact that with an SDX, it's all software, so it's infinitely expandable, infinitely unlimited, and you could do whatever you want. So yes, through SDI, software-defined networking infrastructure, you have these slice exchanges. So imagine, if you will, a bioinformatics researcher going into an environment saying, I want to see spread out before me all my data worldwide, all my tools, all my analytic engines, all my everything, right? And not worry that there's even a network that exists. Not worry that there's an exchange there. It's just one fluid environment. You could do that with this SDX, and that's what we're building toward. It's not production yet, but we're moving it toward production.
A small additional question. Would you also allow other connectivity than layer 2 VPNs, for example, layer 1, for example, layer 3 preferred? Or?
Yeah, that's another good question, because our background is one in layer 0, layer 1, layer 2 development as opposed to layer 3. So definitely a big yes to 0, 1, and 2, because that's where NSI got started, Lambda Exchange, right? We do a lot of work with layer 2 provisioning. With layer 3, the answer there is yes too, except we don't do a lot of that. But we work with people that are doing layer 3 tunneling of various types, and it perfectly maps. And SDN gives you a very, very rich set of tools to define flow specifically into flow spaces using not just destination addresses, but source addresses in, infinite numbers of combinations. You can almost say The issue here with SDN is we have too many tools and too many options because it's infinitely rich.
That's software, you know. You always have
exactly. So this is the big revolution, going from network as basically hardware with a little bit of software there to basically software with some hardware resources someplace. But you're really concerned with that software. It's a great revolution.
Thank you.
Thank you.
Thanks. Anyone else? I have a question looking at this diagram. Maybe it's for you. I'm not sure who of you will be. It's about the, again, I made a similar question in the previous session. It's about the security model. When you put here the OpenStack cloud, the collaboration among the different sites are based on the OpenStack access control, or are you using something different? You can come here.
The short answer is that we haven't gotten there yet to really work with that very much. We're not exactly sure what the best security model for working with the OpenStack clouds particularly and virtualized applications in general with the software-defined networking.
So SDN gives you an opportunity for two things. One is significantly more enhanced security and absolute disaster. You have both options because you're creating control channels that not only are control channels for network operators, super secure and all that, but control channels where you're saying, I'm handing this off to whoever wants it. Not willy-nilly, it's under policy, but still, you're giving away control channels to resources. So it's a tricky business. And
so it's all the rope we're ever going to need.
It's all the rope you'll ever need to hang yourself. But you see this sort of happening in the Genie environment, where Genie is a distributed environment where students are creating their own national, international networks using their own protocols. So some are saying, we don't like TCP, we don't like IP, so we're going to do whatever protocol we want. Those are personal networks. So they're creating personal national, international network. This is going to escape from the computer science community to the wider community. Good luck to all of us. Security? Well.
No, but
I guess the other thing that I should point out is most of the projects that we've been running in our OpenStack clouds, they haven't really required a high level of security. So there's been nothing that's really demanded us to address a lot of the high security issues.
yeah, but when you start thinking about commercial interactions and this kind of stuff, I mean, which is, I'm not criticizing the approach. It's better to show that what you're able to do, and then, well, but you have to be aware that this is the kind of task that you should, engage with the sooner the better. And this is simply that. And I was curious if you were running some kind of experiments already or not, if this is in your agenda for the future.
Yeah, not yet. I mean, I think the security is a serious concern. It's just hasn't come up to the top of our priority list. So.
Okay.
Okay, thank you.
So, thank you so much. Well, our next speaker is precisely going to talk about another key kind of application, which is precisely about security. Security, come on. Traffic engineering is Jasona Astorga for the University of the Basque Country. So. You don't have your
No, I will use this.
Okay. No, sure.
So my name is Jasona Astorga, and I'm going to present the DIMPAC framework, which is the outcome of the DIMPAC Open Call project. The main goal of DIMPAC is to provide disruptive layer 2 end-to-end connectivity services, like, for example, Giant Plus on top of a pure SDN OpenFlow infrastructure. That is, DIMPAC allows users to request bidirectional layer 2 services and with a guaranteed bandwidth. For that aim, DIMPAC implements a novel traffic engineering algorithm. In fact, all of you know that traffic engineering is one of the most promising applications of SDNs, mainly because of two reasons. On the one hand, having a centralized control plane allows taking routing decisions better informed, having real-time knowledge about the network topology and monitoring information. And on the other hand, the programmability functions of SDNs allows to automatically program in the network devices the routing decisions taken at the control plane level. So, this novel connectivity service will provide a lot of benefits both to networks and to network administrators. First of all, thanks to the logically centralized control plane, network monitoring will be improved, as it will be possible to have real-time information about the network state. And also, thanks to this, it will be able to make a better use of network resources. Additionally, also, DIMPAC also provides resiliency against network failures and quick response times in case that a link goes down, in case of a service disruption. Because DIMPAC allows to detect network failures more easily and to react to them. As already mentioned, thanks to the programmability capabilities of SDN, DIMPAC also allows to save cost in operational management, as services can be managed completely automatically. So traffic engineering is not a novel research issue in data networks, and so far quite a lot of algorithms have been proposed based on the minimum cost multi-commodity flow problem. The main goal of this optimization problem is to compute paths between two endpoints of a data network while meeting traffic demands, minimizing network congestion, and also optimizing the utilization of network resources. The basic idea behind many of the proposals, or all of them, is to split traffic over multiple paths between a given source and destination pair. However, although it has been extensively proven that this multipath routing allows to make a better use of bandwidth compared to the commonly used shortest path first algorithm, in reality there are not a lot of implementations of such multipath routing algorithms. The main issues common to these proposals is that on the one hand, usually they require to split traffic arbitrarily and instantaneously at any point in the network, which is not easy to achieve in practice. And on the other hand, traffic or packets route over different paths usually suffer different delays, and therefore reordering must be performed in the destination entity. At this point, it's worth mentioning one success case, which is Google's implementation of a centralized traffic engineering deployment in its before private one. With this deployment, Google has achieved to increase the use of their links from, I think it was about 40% to an 80%. And to save a lot of money this way. But the algorithm they propose is well, it's very adapted to Google needs, and they benefit from a priori knowledge of incoming traffic demands and full control of the network. So what DIMPAC provides is the ability to dynamically compute paths between two endpoints in the network. And also, DIMPAC is a very powerful tool to make an efficient use of network resources, because it allows to make room when a new service is requested. It tries to make room for the new service, either moving already established flows or even trying to disaggregate, to split ongoing services, and to move the resulting subflows, which being smaller, are more easily accommodated in the network. DIMPAC also provides network resiliency and quick response times to network failures. In order to achieve short response times, DIMPAC uses pre-computed backup paths. We compute totally disjoint paths from the primary path, and it distinguishes between two types of services, regular services and gold services. The difference between both of them is that for gold services, bandwidth is reserved, while for regular services, no bandwidth is reserved for backup paths. So the backup path might be only implementable if enough resources are available in the network. As I have already mentioned, thanks to the use of SDN, the operational cost can be reduced as service management can be automated. And we also improve network monitoring by implementing a monitoring module which obtains real-time information about the network state with a flow level granularity. So the DIMPAC framework has been implemented using a modular and flexible approach, and defining standard interfaces between the modules it consists of. In fact, the DIMPAC framework consists of 6 modules, which are the DIMPAC graphic user interface, the monitoring module, the DIMPAC Service Manager, DIMPAC Rules Manager, PCE, and DIMPAC RP Handler. DIMPAC also implements an interface to an external entity, which is an entity which categorizes traffic, and we have called it the Traffic Pattern Analyzer. We have developed DIMPAC based on the OpenDaylight network controller, which is a powerful SDN controller, and which provides multiple southbound interfaces, among them OpenFlow 1.3. And for the implementation of the DIMPAC modules, we have reused some of the functionalities or some of the modules provided by OpenDaylight. Okay. The DIMPAC Service Manager is the core module of DIMPAC, as it acts as a coordinator between the rest of the DIMPAC modules. When a new service is requested from the graphic user interface, the graphic user interface tells the DIMPAC Service Manager about the characteristics of the new service. Basically, it tells which are the endpoints, the source node and port, and the out port and node. And it also informs about the bandwidth that should be reserved for the new service. The DIMPAC Service Manager tries to accommodate the new service in the network without affecting already established flows, but in some cases it might not be possible. In that case, the DIMPAC Service Manager tries to move already established services, the whole flows, without splitting them, to other locations, to other alternative paths, in order to make room for the new service request. But maybe that is also not possible. So the impact service manager goes a step further and tries to split ongoing services into smaller subflows, which being smaller are more easily accommodated in the network and can be more easily moved to alternative paths. All of this with the final aim of making room for the new service request. The impact service manager also listens for topological changes, and if it detects that a link goes down, it identifies all the services that are currently being provided through that link and moves all those services to their pre-computed backup paths. The impact service manager also communicates with the impact rules manager in order to tell the impact rules manager which control messages should be sent in order to program the network devices. And it also performs scheduling functionalities, since different services have different durations and there won't be always the same amount of services or the same combination of services in the network. So in order to manage the different network states during time, we defined what we call network snapshots. A network snapshot represents a group of services which are concurrently routed through the network. So in the example, at the beginning, we have just service A, and service A constitutes a network snapshot. Then another user, or the same one, requests another service, which is service B. And service B starts before service A and finishes during service A. So, as a consequence of introducing service B in the network, 3 snapshots are computed. In the first one, just exists service B. In the second one, coexist service A and B. And in the last one, we have just service A. So when the impact service manager has to introduce a new service in the network, it has to check that there is a positive solution or that the new service can be provided in all the network snapshots that it affects. And maybe the solution might be different. For a snapshot, maybe it requires not having to do anything, not having to move any service. And for another one, it might be necessary to move some services. For a third one, it might be necessary to disaggregate some traffic. The solution doesn't have to be the same. For its functionality, the impact service manager manages independently network snapshots and services, and it maintains 2 databases, one for snapshot management and another one for service management. In the one related to snapshots, it stores information about the start and end time and basically about the services that are provided in that snapshot. In this, with regard to service management, it stores whether its service is a gold or regular service, and it also stores the different links each service is routed through, or the path of each service. So when a link goes down, it is able to easily identify all the services that are affected by that network failure. The path computation element, well, we have implemented our own path computation element, but it could be, the impact has been implemented in a very modular manner, so it could be replaced by any other algorithm. In our case, this element computes first at boot up time all the possible paths between all possible ingress and egress points in the network. And the impact service manager, when it has to accommodate a new service in the network, it queries the PCE for all the possible paths between the source and destination points. This path computation element implements also the traffic disaggregation algorithm. This traffic disaggregation algorithm is only called when there's no possibility to accommodate the new service in the network, not without doing anything and not by moving established flows, just by moving them. We understand that in operational networks it's better not to move traffic or the paths through which traffic is forwarded. So this disaggregation algorithm prioritizes not to have to split traffic, or it tries to split the lesser it can. So it identifies which path is closer to the required bandwidth and starts trying to move or to disaggregate traffic in that path in order to make room for the new requested service. The DIMPACT Rules Manager is the module that translates the control actions computed by the DIMPACT Service Manager to real OpenFlow control messages, and it is based on the ODL Flow Programmer service. The DIMPACT Monitoring is the module in charge of providing real-time information about the network state as the users request services specifying a guaranteed bandwidth, a desired guaranteed bandwidth. It is mandatory to monitor whether then these services comply with that requested bandwidth or not. So we have a monitoring module which tracks flows that are far from their maximum allowed bandwidth, are monitored at a slower pace, and when they get closer to their maximum allowed bandwidth, they are monitored more quickly. So this monitoring module is based on the statistics messages of OpenFlow 1.3, and it makes use of the statistics manager module of OpenDaylight. Then we have an ARP handler module, which avoids having to insert unnecessary ARP-related entries in the OpenFlow switches, and it replaces the ARP handler module of ODL. The DIMPACT graphic user interface has been introduced in ODL as an extra tab to the ODL GUI, and it allows to request and delete services. In order to request a service, the user must specify the source node, destination node, and the ingress and egress port, the start time, end time, and also the bandwidth. Other information, such as, for example, MAC addresses, could also be provided but are not mandatory. And the DIMPACT framework provides also information about the requested services, whether they are reserved, they are activated, they have been deleted, etc. So for you to have an idea of how DIMPACT works and what it looks like, I'm going to play a short video in which we saw a little demonstration of DIMPACT.
Welcome to the Dynamic Path Computation Framework demonstration. Welcome to the Dynamic Path Computation Framework demonstration. DIMPACT is a giant open code project led by the University of the Basque Country. One of the main features of the DIMPACT framework is that it provides resiliency. In DIMPACT, gold services are guaranteed with a backup path. In case of link failure, this backup path is automatically installed on the network. Here you can see the topology that we are going to use to demonstrate how the resiliency works in the DIMPACT framework. First of all, we are going to check that there are no flows installed in the devices. This way, when we request an impact service, we are going to see how it automatically programs the devices on the network. In order to request the impact service, we need to specify a name, and we also need to select the source and destination nodes and the ingress and egress port. We also need to specify the duration of the service. The impact is going to check if there are resources available for the requested service in the entire period of time that we specify. We also need to select the bandwidth that we want for our service and specify the source and destination MAC addresses that they are going to use to characterize our service in the network. In addition, we can also select if we want this service to be a gold or regular service. As you can see, the service has been requested. And if we go to the DIMPAC terminal, we are going to see how this request has resulted in the generation of a new snapshot for this specific service, called Service Backup. Now we can check how the service has been properly installed in all the devices of the network. DIMPAC selects the shortest path for the services. So in this case, the service has been installed in the switches 1, 6 and 4. If the link between switch 1 and switch 6 goes down, the DIMPAC automatically reacts and installs the new service in the network. Now, if we check, we can see that there are no flows installed in switch 6, and instead, flows have been installed in switch 2 and 3. The DIMPAC framework supports service scheduling, thanks to its time-dependent resource consumption awareness. In this second demonstration, we are going to show how the different snapshots are generated in the DIMPAC framework. We are going to use Postman for quick service request. First, we are going to reserve service A. If we go to the DIMPAC terminal, we can see how the snapshot has been generated. Here we can see that only service A exists in the snapshot. Then, if we request service B1, we are going to see how a different snapshot has been generated, which includes service A and B1, maintaining the previous snapshot, now divided in two, where only service A exists. If we do the same with services B2 and B3, we are going to see how the three services are requested. These services are using the same resources, but they are doing it in different time slots. DIMPAC is clever enough to figure this out and creates different snapshots. We can see how in these new snapshots, service A and B2 exist, and service A and B3 exist, but B2 and B3 never exist together. Finally, if we request a service C of the same duration of service A, we are going to see how all the affected snapshots are updated. In order to optimize network resource utilization, the DIMPAC framework implements a flow disaggregation algorithm. For this demonstration, three services have already been requested to the DIMPAC framework. Service A of 8 gigabits, service B of 5 gigabits, and service C of 7 gigabits. DIMPAC assigns the shortest path to the services, taking into consideration the resources available in the network. Service A goes from switch 1 to switch 4 through its shortest path. Service B goes also from switch 1 to switch 4, but from an alternative path, and service C goes from switch 2 to switch 4. We can check how the flows have been programmed in the network devices. In switch 1, we can see how the flows of service 1 and service 2 are installed. We can also check how in switch 2 the flow entries of services B and C exist. With this situation, if we request a service D from switches 2 to switch 4 with 9 gigabits per second, we don't have enough resources in the network to allocate it, unless we disaggregate. In these cases, the DIMPAC framework calls the path computation element and studies how the services installed in the network can be disaggregated by using the information available through the traffic pattern analyzer interface. In this situation, the path computation element is telling us that by disaggregating service B, we can make room in the network to allocate this new service. Now, if we check how the devices are programmed, we can see in switch 1 that service B has been disaggregated into 3 different sub-services, thanks to the OpenFlow granularity. And now we are able to allocate service D.
So that's all. Going back to the presentation, well, now that you figure out how DIMPAC works, we just wanted to show some numbers about the performance of the framework. At this point of our implementation, we are not worried about performance because we are more worried about functionalities, about developing a modular, flexible implementation which is easy to adapt, to modify, and we know that performance can be improved. We are aware of some operations that can be performed in parallel, etc. But we just wanted to give some numbers to show that the performance, even without optimizing it, is acceptable or it's quite good. So, as a conclusion, DIMPAC provides layer 2 connectivity services between endpoints in a network, guaranteeing requested bandwidth. DIMPAC also provides or optimize network utilization because it is able to move already established flows or even to split these flows in order to make room for new services which otherwise couldn't be provided in the network. It implements resiliency through the pre-computation of backup paths, totally disjoint backup paths. It also implements real-time monitoring with flow level granularity, and it allows reducing operational cost of service management as all the life cycle of the services in DIMPAC is managed completely automatically. So, thank you for listening to me.
So, do we have any questions? Oh, two in the row. So no, wait till ladies.
Hi, I'm fascinated by the way you rearrange a running flow if there's a lack of resources. Have you tested what the impact on an actual end user is when you suddenly route his traffic somewhere else? How long does he lose packets? How does his flow recover if it's, say, a long TCP connection, for instance? Do you have any data on that?
Do you mean when we have to move ongoing services to alternative paths, the impact on end users?
Yes.
I think that, well, we don't have numbers, but in the tests we have done in our network for the end user is unperceivable.
Sorry?
It's unperceivable. The end user doesn't realize about the disruption.
That seems very unlikely. You're bound to lose some packets, so you get some TCP slowdown and then needs to ramp up again. And on a long distance link, that could be fairly disastrous.
We haven't tested it formally, so we haven't performed tests to measure the delay, for example, that would take to since the last packet goes through a path until the next packet goes through the new path, for example, or the number of packets that are lost in that period of time. But our impression when doing the test is that performance is quite good, but I can't give numbers.
Okay, thank you.
We had another one, yes, over there.
I have two questions. The first one is, if we wanted to try and experiment with this stuff, is it available as open source, or is there a way where we can at least use it, if not develop on it?
Yes, it's available at the Giant repository. I can't provide you the URL right now. I don't know it by heart, but I can tell you afterwards.
Okay, great. And my second question is for the traffic management aspect of this. Are you provisioning metering of flows, and is that done with OpenFlow, or is it some sort of out-of-band mechanism? Do you do multi-table OpenFlow?
We are using OpenFlow 1.3 in order to provision the services, yes.
Okay, and you're using the meter tables from OpenFlow in order to control the flows?
Which table, sorry?
OpenFlow has this mechanism called meter tables.
No, we are not using them, no.
Okay, thanks.
Mm-hmm.
No more questions. We are doing extremely good in time, so thank you.
Thank you.
And next speaker, despite having lost his badge, a second. Is Rod Wilson from Siena, and he's going to introduce in general agility for SDN apps or app-centric networks. And according to the summary, he's going to talk about my favorite issue in the last couple of years, which is NFV as well. So you're most welcome.
Okay. All right, thank you very much. So my name is Rod Wilson. I work for Siena in our CTO research group in Ottawa, Canada. And it's my pleasure to be with you here today. The previous speakers spoke about SDN applications and an environment that is creating great flexibility within networks. My perspective, working for Siena, is to describe how this is impacting some of our network and product design initiatives and some changes that are being incurred in the behavior of Siena and the way we're developing products. Does anyone know what this map is? Have you ever seen it before? It's actually Facebook's use map. And you can see how popular Facebook is in some countries and other countries where maybe it's less encouraged. And of course, these are technology trends, and if we wrap around a large assortment of buzzwords around this, the takeaway is that there's a huge amount of change, but the change is all happening around network flexibility and making networks more dynamic, more responsive. And this is a very different approach to traditional ways of building networks. So we used to build networks, that looked like this. We used clouds, even decades ago. You'd open a brochure and there'd be a cloud in the middle of the brochure, and then various boxes and lines connecting to the cloud. And they would be defined as intercity or long haul or submarine or regional, and you would have edge, metro, and backbone. And of course a wide selection of products in there. And these were often hierarchical, so you would use edge products to connect the edge to the metro or the regional network, and then longer haul for the backbone to create intercity or intercontinental networks. 80% of Ciena's business is to service providers, and this has been the service provider model for decades. But networks are becoming agile, and these architectures are starting to change. The service provider central office is really becoming content centers, and these are necessary for the flows of over-the-top services, things like Netflix and so on. And the expensive network functions are becoming virtualized, and the previous two speakers spoke quite nicely about that. The ability to do new and dynamic provisioning, and the ability to switch flows according to what the application requires. So networks have to become agile because of the new users and new applications and the demands it's placing on the network. And so when we look at SDN, we're using SDN principles to actually increase flexibility within the networks. So a traditional model, of course, had network management and OSS services that would provision a network and then monitor its performance and either manually or automatically change the network. And the network, of course, had this combined control plane and forwarding plane, and then local, regional, and backbone distribution. But now we see an emergence of the response to these web-originated or web-scale services, where the control plane and the forwarding plane have separated. And so we start looking at orchestration and control and the requirement for real-time, on-demand control and networks that are, as I say, much more agile. Furthermore, the control and orchestration techniques are outside of a particular vendor or a closed group. They become very open. And this has created a really interesting environment that we see changing behaviors, changing the way people provision networks and the way networks operate. The previous speaker spoke quite nicely about some new provisioning tools and an environment that allows great flexibility from external control. And in the hardware and vending world, this is what we see as well. So users are saying, I want to move 100 gigabytes from A to C for my application, as opposed to a blanket provisioning across network resources. And then between the control layer and the network, you see various conditions that can get employed, and this is exactly what was shown in the previous presentation about defining specific flows within the network. And I think if we look carefully, the little network diagram at the bottom here is almost the same network topology. So that's the environment, and you see industry responding to some of the developments that are happening in the research world. So one of the things that we have to respond with is a much more flexible and open hardware and open architectures to deal with this. So Ciena is changing, and it's a very significant strategic shift. We're on the process of opening the application programming interfaces for our products. We're creating open APIs. So these are based on well-defined interfaces, but also provide powerful integration points. So off-board controllers can look at addressing specific needs, and also providing tools for our partners, for our collaborators. So we've created a development operation focused specifically around a laboratory environment for proving out open APIs to control our products. Now, what might these be? Well, if we look at DWDM applications as one example, we have developed both our own internal applications as well as an invitation for customer apps that are in development that grab onto the APIs. So for example, in our DWDM technologies, we rely heavily on coherent modem, coherent transmission and receive. So there's an internal modem, and it's possible to look at the internal parameters to assist the design and development of debugging of future modem hardware. This kind of thing has never been made available to researchers or even to end customers. So for example, you could look at the pre-error FEC rate. So before it goes through the forward error corrector, what is the error rate performance of a network? What is the signal-to-noise ratio on your network? What is the PMD or other chromatic dispersion impairments? And so the ability to go in and look at that may be useful to some people. Other people may not care, right? So you wouldn't have that particular application. On the photonic line side, things like multi-channel optical power becomes very helpful if you're looking at alien waves or other infrastructures of that type. So being able to deploy over a foreign line system requires some very special measurements. And if this was something that you were going to embark on, these kinds of tools would assist you. And then at the application layer, you see a mashup of optical line and non-technical external derived data. So for example, maybe using OTDR to detect a cable break or locate submarine cable synchronized to GPS. So the information from the cable would actually help guide the ship to where the break has occurred. So these are kind of interesting applications at all three layers of a DWDM system. So one of the things that we've done is create a virtual lab to vet and prove out and help collaborate in the development of these new applications that will create more agile networks. So it's a develop environment designed to help our customers and third-party developers or even researchers create, test, and fine-tune these custom applications. Now, the process is actually underway to open the APIs on a wide selection of Sienna products. And you see a list of products here. The first one on the list is a product called Wave Server, which is a new product that was announced just last month. And it's designed as a data center interconnection device. So on the surface, it's a really boring product. It has a WaveLogic 3 optical modem inside, and it has any combination of 10, 40, and 100 gigabit per second Ethernet on the input side, and on the outside 100, 200, or 400 gigabits. So it's a useful box. It certainly has some capabilities that, as I say, designed specifically for data center interconnection. However, what makes it an interesting, extremely interesting box is the ability to use the APIs and the creation of new handles and knobs to actually control this box, to do some analytics, data collection, and other control mechanisms that may be necessary in your particular application. So in this way, end users can create and test and fine-tune apps that are based on your own needs. And we find this particularly exciting product when we look at research and education networks, because of all the people on the planet, the group most likely wanting to play with open APIs and use them as a tool set to create more flexible, dynamic, and agile networks is probably right here in this room. So a quick look at this Wave Server product. It is capable of up to 400 gigabit per second on the trunk side, and it can have a combination of inputs depending on what your requirements are, but 40, 100, or 10 gigabit QSFPs on the front. And then there are also the ability to have a wide variety of different plug-in modules, and then obviously network management ports and control on the outside. It's not my intention to talk about the product here. If you want to see it, it's in our display area downstairs. But the point of the discussion is really that it's, I think, the first departure of a vendor into the world of creating a highly flexible infrastructure based on programmable products. Many people speak about open networks, networks that invite a lot of different applications, but often these are simply a shell in front of a proprietary system, a closed system. And in this way, we're opening up the APIs and making it an environment that will really allow this to become a programmable platform. And this has been a characteristic that we've been talking about for some time. This is our kind of first proof. So we see the network actually becoming a programmable platform. In the past, provisioning was rigid and prescriptive, and for the past couple of years, using technologies like OpenFlow, or more generically described as SDN, people have shown new ways for platforms to be more flexible, or more products and networks to be more flexible. But we believe that this really should take the next step and become a programmable platform where network connections are fluid and can change dynamically based on application control, and connections that were once rigid are now temporary if they need to be. Obviously, if you need to provision something for a long time and make it more static, of course you can do that. But the trend is certainly more towards these applications that require dynamic, agile networks. So in this way, we can enable network-specific applications, network-enabled applications. We've done some interesting demonstrations most recently that used a multi-touch table, sort of like a giant iPad, to configure not only the network infrastructure, but to also take slices of compute power and then graphically or through manipulations on the table cause a network reconfiguration and a virtual machine migration at all three layers in the network. So this is possible because of a programmable infrastructure. And we will be undertaking work with our partners that will see that become more of an application control rather than a user and a touchscreen control. So it's network driven and reconfigurable SDN. So, you know, we've often heard the phrase, there's an app for that. We start to think that there's a network for that, whatever that is. We regain control of real-time consumed network resources. The bandwidth problem arguably has been solved for many years, but the control of that bandwidth is something that is only becoming truly addressed now. Cloud content centers, we really have to make distance disappear at a massive scale. And these kinds of technologies allow that to happen. And network function virtualization is there to increase service deployment velocity and reduce complexity. And with that comes reduced expense and, of course, higher performance for our users. And so that's my talk this afternoon. Thank you very much for your attention.
Well, amazing. In time-wise, probably we will be free to go look for some coffee earlier than anyone else, and that's good. Any questions? Any comments? Please. No, wait.
What is the mechanism by which you switch data flows among different optical channels? I mean, do you have something like a G709 frame switch in those devices?
In that particular device, there's no switching capability in that particular wave server device. So I should be clear that at this point it's designed primarily as a feeder box. In the future, we will be able to do switching in that, but more generically, the environment that we've created uses traditional optical switching, but that's based on our 6500 system and other line switching equipment that's installed. We have an 8700 layer 2 switch installed in Starlight in Chicago. We have another one installed at the University of Amsterdam, as well as in our own facility. And so these become the flexible platforms and the switching environment that I was referring to. Okay. Thank you very much.
Well, thank you so much, Rod, and the rest of our speakers, and thank you for being here. See you soon.